before coming to Finland 2 years ago, I had a similar project in Australia in plantations where basically we were testing how well the operator was doing the thinning, the tree selection, and I noticed there was a lot of rule of thumbs when he made decisions. So, and and we have LiDAR now, we have better technology to actually capture data. And I thought it would be a much better way to, to do the job. And these people, remember, they are working for 8-10 hours in the forest. They're making very important decisions, but our human brain cannot handle all that information. So now we have the opportunity to use LiDAR, to use optimization and things like that. So. And as I mentioned before, my background is in forest engineering, but I did my master in operations research and optimization mathematical models. That's something I'm going to show today, what we are doing with our PhD students here in Finland at Luki. So this is the outline of my presentation. I don't think I'm going to spend a lot of time in the introduction because most people have already talked about that, the role of thinning and decision parameters. I'm going to focus more on the what we are doing in terms of the tree selection. Also, I'm going to touch or talk about uncertainty. In forestry, we have a lot of uncertainty, and I'm going to show one approach to deal with uncertainty in our planning models. And then implementation and how we can integrate that in an operational context. So that's the synergy and the connection with what Carrie presented, and some policy and market relevance. Yeah, so here, Yevgeny mentioned, Carrie mentioned already that thinning in Finland and the forest cover is quite important in Finland. So more than 70% of the forest cover is forest, and they play a key role in national climate targets. We have a commitment to carbon neutrality by 2035, and forest thinning is a common management practice. All the forest owners, they do thinnings, but mainly focus on timber production and not on carbon production or sequestration. So yeah, climate smart forestry requires smart thinning decisions, and this is the focus of this project. And I found this slide, which is very interesting because this is what happened in Finland in the last 2 years. So we passed from being a country which are capturing carbon to we are emitting more carbon than what we are sequestering. For many reasons. One reason could be, the trading issues with Russia. Now we are doing more thinning, more intervention in Finland. In the past, we were importing more wood from Russia. Logging could be one reason, but also the loss of growth, climate change, many things explain that situation. But this is a challenge for Finland. So we passed from being a carbon sequestering country to we are emitting more than what we are sequestering here. So, and you can see the figures in 2020, for example. Yeah, it was a big amount of carbon sequestered, and now it's a little amount of what we are sequestering in Finland. So this is a challenge for Finland. And so traditional goals and new challenges. The role of thinnings, the purpose has been traditionally to reduce competition, to improve growth, increase wind resilience, and typically based on a spacing or DBH threshold or basal areas, things like that. Very traditional sort of way to do thinning. And but carbon impacts are often not explicitly considered in that decision making. And as I said before, current thinning practices optimize for growth and timber. That's the traditional way to, the objective and the goals. And so now we move from a rule-based to a goal-based decision making. So now we have the opportunity to combine remote sensing, LiDAR, and optimization method for improving the tree selection. And we are using mathematical model to actually select individual trees for removal. And the objectives are to maximize long-term carbon storage, minimize operational harvesting costs. Remember, we are doing the thinning that costs money, a lot of money. It's a quite hard operation, quite difficult operation. So in one hand, we have to optimize, the goals of the forest owners, but on the other hand, we have to do the thinning that costs money, and we have to, make an operation profitable for the logger. And also, we have to maintain or enhance forest productivity. Okay. I think Carrie showed this image before that was developed by Ponce. This is the solution by Ponce. So in the Ponce interface, you can see this. The LiDAR is scanning around 20 meters around the machine, and you can see patches of trees, and then the operator see this image on the tablet, and he can make decisions. What we are proposing now in our approach is doing something a little bit different. It's not only to show what is going on around the machine, but also to tell the operator which tree should be removed in real time. So all the green dots are trees that should be removed. To do that job, we need to do the optimization beforehand. Okay, and we are going to pass that solution to the operator in real time. So that's basically what we are proposing. So what drives a good decision? Well, this is not new, but some of you have already mentioned all the parameters, but we have a number of those. So, DBH, height, species, crown class, health, vigor, harvesting cost, spatial location, stand extraction, and risk factors. And how we can capture all of this data. So we have here data sources and methodology, and you can see from the data can be collected from field inventory, LiDAR, from the harvesting head, as Kari mentioned, from growth model. For example, in Finland, we had MODI, the MODI simulation model, from remote sensing, visual inspection, different harvesting productivity model, GPS, LiDAR, and all the remote sensing techniques. And here you can see in the middle, what is the role of this parameter in optimal selection? Just to mention a few species, for example, affects growth rate, carbon allocation, rotation length, DBH, predict biomass and carbon and growth potential. And then, of course, we had harvesting costs, affects the economic feasibility of thinning operations, the spatial location determine machine access and cluster optimization, and so on. And then risk factors. I'm gonna talk a little bit about uncertainty and risk factors. For example, mortality, windrow, and pest damage. Okay, so those are some of the parameters affecting decisions. And also, just to set the context of what we are doing in this part of the project, so we are focusing on what I mentioned before, optimization, and what is called stochastic optimization. This is optimization when we include uncertainty, okay? So now we are in a climate change sort of situation where you have pests, you can have damage by fire with a certain probability. Okay, so how we include that uncertainty in our planning model was using this sort of mathematical techniques. I'm going to show that in a moment. But you can see here all the spectrum, the data analytics spectrums. This is, for example, from descriptive analytics. So, for example, you have a machine and you want to know what happened with the machine. Well, the machine did this. Okay, that's descriptive. But then we pass to the next level, diagnostic. So why did it happen? Why that machine had that productivity or a low productivity or high productivity? Well, we want to try to understand what happened with that. And then we want to predict what's going to be the productivity of that machine in the future in a certain conditions. And this is where we apply predictive analytics. And when you hear about AI mainly focus on this, developing prediction or prediction models. So we are here with the traditional AI. But here, possibly not many people don't know that optimization is also part of AI. But in this case, we are, it's the only approach where we are actually providing a new way to do, an optimal way to do things. Here we are just predicting. Here we are providing a course of action. What we should do, how I should thin my forest to maximize carbon sequestration. Okay, and here is the same, but under risk. Okay. And you can see here that when we move from descriptive to prescriptive analytics, well, obviously our models are much more complex, but at the same time, we provide a much better competitive advantage for the organization. So that's basically the trade-off. We are developing more complex model, but this model provides more competitive advantage for the different organizations. Now, in terms of optimization, there will be some equations here. I'm not going to dive into the details of those equations, just to mention what we are doing. So basically here, we have to decide whether or not a tree should be removed during the thinning operations. So that's a variable, And we want to maximize the carbon potential. We have many trees in the forest, so that's eyes, only one tree. So we have many eyes, many trees. And we want to maximize the carbon sequestration of, or the carbon potential when we do the thinning. So that's basically what we are doing. So we want to maximize the long-term carbon sequestration. The model is going to tell us which trees should be removed in the forest. So, for example, here we have just a visual representation of the model. And the challenge here is how we can develop a carbon potential, this parameter. That's the key element here. We need to develop this parameter for each tree. What sort of factors we are going to consider for developing that parameter, because that's crucial for doing the optimization. But also we have restriction, we have constraints. We want to maximize something, but at the same time we have restriction or constraints. We have stand density and spacing constraint. We have operational feasibility. When we do the thinning in the forest, we have some operational feasibility, for example, terrain, machine limits. Carrie also mentioned some of those sort of restrictions and issues. And optional, we have to also achieve some harvest volume targets, and we have obviously budget limits. Sometimes that's the main limit is the budget. We could do better, but it could cost more money, and we don't have that money to do the change. And so the carbon potential could be derived from tree species, DBH, growth projection, mortality risks, and carbon retention lifespan. Okay, these are some of the factors that could be included in that parameter. But that's something we need to discuss more with ecologists and silviculturists. Okay. In the past, also, I already did some modeling test. This is in southern Spain for pine plantations. So we published a paper just a few years ago on trying to determine what is the impact of the carbon price on thinning scale. So we are optimizing thinning. This is at a large scale for 600 stands in southern Spain. And we wanted to know how carbon is going to affect that thinning scale and the net present value in that sort of plantation. And it was very interesting when you start increasing the carbon price, how the thinning starts changing, especially in this case, we were maximizing income from timber production, from biomass production, but also from carbon. Okay, so we start playing with the carbon price and see how all the thinning strategies start changing, and how everything, especially changing. That was very interesting, and how our ability to deliver the timber to the different mills change. Because of course, if you want a better carbon price, you will delay the harvest of the forest, and that's going to create other issues. For example, we won't be able to deliver the timber to the mills. And so if you want to see this, I was published in Forest Ecology and Management. And it would be interesting to do something similar here in Finland. And then in forestry, this is even more complex because it's not only about one objective, maximize carbon or maximize timber. For example, here you can see that we have at least two objectives. In one, we want to maximize carbon, but on the other hand, we want to minimize harvesting costs. Okay, so we have two different objectives. And how do we deal with that? Well, using these techniques called multi-objective, or in this case, it's bi-objective, because there are two objective modeling or optimization techniques. And so we can do that. We can handle this. And again, here a variable, we need to decide whether or not we are going to remove a tree during the thinning. We have the carbon potential for that tree, and we have the harvesting cost for that tree. Okay, so we put that in the objective function. And again, we have several constraints. And and in the end, what we have is something like this. We have the Pareto frontier, the Pareto curve. Okay, so we had harvesting cost here, and we had carbon sequestration. And here you can see this is the solution that maximizes carbon. We are here. It's very expensive. On the other hand, we have a solution that minimize harvesting costs, but you can see the carbon sequestration is quite low. Okay, and we have a lot of solutions in between. It's up to the forest owners. It's up to the forest planner which solution we are going to implement in an operational context. Okay, but this is the type of solution that we can get from the previous model, from this more complex multi-objective optimization model. Okay, the Pareto frontier. And again, I'm not going to explain the equation, just to say that now, because of climate change, we are dealing with risks. We are dealing with uncertainty. Imagine you are managing a forest that in the next 10 years, you're going to have forest fires with a certain probability. Okay, 10% with this sort of damage, 30% with this sort of damage, or whatever. You have different type of damage with a certain probability. How do you deal that when you're doing the planning? And this is very relevant for forest planners. Imagine you have to plan your intervention for the next 50 years, and you have climate change thing, you have risk, you have uncertainty. Okay. Again, there is a mathematical technique to deal with that. It's called stochastic programming, and typically you make decision in what is called 2 stages. In the first stage, for example, you can decide when to do the thinning for different stands in a 20 or 50 year period, or 20, 30 year. And in a second stage, you have other decisions to make. That basically decisions here in the second stage are made when the uncertainty is revealed. And in the first stage, we are making decision when the uncertainty is still not revealed. And so here we try to make decisions that are going to minimize the cost given that the solution that you make in the first stage. Okay, so you combine, for example, in the second stage, here you are implementing a thinning decision for different stands, and here in the second decision you can adjust the thinning intensity, for example. So in the first stage you say when to do the thinning. In the second stage you say with which intensity I do the thinning for each stand. So you can modify your harvest schedule, and you can allocate for disturbance intervention or carbon reporting correction. Okay, so here we have, these are the first stage decisions that we made today, and then in the future you have scenarios with different probabilities. So in the end you have like the expected value of those decisions because you have too many scenarios. Okay, and so it's basically the average solution for the second decision for each scenario that you have. And the idea is to minimize all of that or maximize. Okay, so I know this is a bit more complex than what I show with the multi-objective optimization, but this is how we can deal with uncertainty. And for the implementation, for example, this is for Finland. We have several tools. We have several organizations that can provide the data, remote sensing, inventory, and organization that can provide the data. We have tools like Prevas or Modi for carbon growth or growth modeling, and also harvesting the APIs for feedback and monitoring. And this is what we are doing with my students at the moment. So here, again, we use LiDAR sensor. We scan all the forests beforehand. So you have something like this. The location of each tree, the diameters and things like that. We run our optimization model. And so here the model, each red dot is where the machine is going to stop to pick up the trees. Okay. And what is the optimal trees to be picked up? Those trees are the optimal solutions. But also in our solution, we tell from which position those trees should be cut. Okay, so all these red dots represent where the machine stops to grab the trees. Okay, which trees? Well, the one that were determined by our optimization solution. So, and then in the next phase, we are also optimize the road location. So basically, the thinning road location will do something like that, very similar to what Carrie showed here before. I'm using Carrie's picture. But basically, you have a machine that is it travels, in the forest, picking the right trees, the optimal trees, and also optimizing the road location of the. So this is how we implement the solution in real time in an operational context. But what we are doing is to develop, first of all, a planning tool. Imagine we have this interface for the forest owners. So you will have a menu here. You can change your parameters. For example, you are the forest owner. You want to maximize timber. Well, I change my parameter, and the model is going to show you what is the solution for that sort of goal. But on the menu also, you can maximize carbon sequestration. And again, you click that, and the optimization model is going to provide the solution for that to meet that goal. And then when we are happy, when the forest owner is happy with the solution, we pass that solution to the operator in a real context. And then he doesn't have to actually in the forest, look or spending too much time, visualizing the trees, because he already know the optimal solution. It's just a matter to put that on a tablet, on a visual interface for him, and to be able, to pick the right trees. But we already know what is the optimal solution, okay? And then, well, so Carrie already showed some of these systems that was developed by the Swedish company. It's the same system as the Ponce system. So a LiDAR sensor scanning the trees around the machine. That's the interface, by the way, for the operator. And then in the future, we think it would be technology like this one, AR, virtual reality, augmented reality, for example, using goggles. And it's going to tell the operator where, to travel, which trees to pick, because we know the optimal solution. It's just a matter to identify the trees here in the goggles or in the tablet, and he will be able to pick the right trees according to the optimal solution that we are providing. Okay. I'm not going to talk much more because you already talked about that, and Evgeny and Viles. So, but basically, we need incentives, and this is the incentives we are maximizing. We have a market now. We have a carbon price. We have a strategy at a national level and European levels. And carbon-oriented thinning could be tied to voluntary or compliance carbon markets. And also there are opportunities for ecosystem service payments and blended finance models. Okay, so it's to me this picture is it shows all the forest owners, but because this is something we are targeting with the solution we are developing. It's something that had to actually have had several discussions with my colleagues. And remember here, we want to maximize the benefits for the forest owners, but on the other hand, we have to do the thinning, we have to do the operation, and sometimes there are conflicting objectives. Sometimes providing the best silvicultural solution is very expensive to implement in the forest. Okay, and here we have sometimes a conflicting sort of interest, and but at least this model is going to show you. Remember the Pareto curve is going to show you all the potential solution. It's up to the forest owner and the logger to determine, mainly to the forest owner, to determine which solution he's going to implement in real time or in a real operational context. That's it. Thank you.
Good.